Section 770 of the National Electrical Code covers optical fiber cables and related materials. The code does not explicitly prohibit the installation of Innerduct in an exposed configuration like between equipment cabinets. However, the NEC requires that optical fiber cables and their associated components be protected from physical damage. This protection can be achieved through various means, including firstly enclosing the optical fiber cables in a conduit, like electrical metallic tubing or rigid non-metallic conduit, secondly suspending the optical fiber cables in a cable tray or trough, and thirdly burying the optical fiber cables underground. When considering exposed Innerduct, even though the NEC doesn't explicitly prohibit it, there are several factors to consider before using this method. Physical damage is of primary concern. Exposed Innerduct is more susceptible to physical damage from objects falling or bumping into it. This could damage the Innerduct and the fiber cables within it. Environmental conditions also play a role. Exposed Innerduct can be affected by moisture, dust, and sunlight, potentially degrading the Innerduct and the fiber cables over time. Aesthetics are another factor. Exposed Innerduct may not be aesthetically pleasing in a finished space. Given concerns about physical damage and aesthetics, it's recommended to follow the engineer's request to run Innerduct between the equipment cabinets, but with certain precautions. Firstly, securely support the Innerduct by using straps or hangers to securely support the Innerduct from exposed I-beams. Secondly, protect the Innerduct from physical damage by installing conduit caps or other protective measures to prevent objects from falling into or bumping into the Innerduct. Thirdly, consider using a flexible Innerduct, which is less likely to be damaged from bending or movement. Fourthly, if possible, install the Innerduct in a concealed location such as along the edge of the room or in a way that minimizes its exposure. By following these precautions, the risks associated with exposed Innerduct can be mitigated and the integrity of the fiber optic cables ensured. When installing Innerduct, selecting the correct type and size is essential for protecting fiber optic cables. The Innerduct should be sized appropriately to accommodate the number and size of fiber cables being installed, allowing for future expansion. Materials like high-density polyethylene are commonly used for Innerduct due to their flexibility, durability, and resistance to environmental factors. Ensure that the Innerduct is compliant with industry standards such as ASTM D3485, which specifies requirements for smooth-wall polyethylene conduits and duct for underground installation. This compliance ensures that the Innerduct meets specific performance criteria, including tensile strength, ligation, and resistance to crushing and impact. Securely supporting the Innerduct along its run is crucial for preventing sagging or damage. Support interval should be determined based on the manufacturer's recommendations and the specific installation conditions, such as the weight of the cables and the spacing between support structures. Use appropriate hangers, straps, or clamps designed for supporting Innerduct, ensuring that they are compatible with both the Innerduct material and the support structure, such as I-beams or walls. Proper spacing and support minimize stress on the Innerduct and fiber cables, preventing potential damage or degradation over time. Protecting the Innerduct from physical damage is also essential, particularly in exposed environments where it may be vulnerable to impacts or abrasion. Installing conduit caps or other protective measures at the ends of the Innerduct prevents objects from falling into the duct and potentially damaging the fiber cables. Consider using protective sleeves or wraps in areas where the Innerduct is exposed to potential impacts or abrasion from machinery or equipment. These protective measures act as a barrier, absorbing impact and preventing damage to the Innerduct and fiber cables. When routing the Innerduct, minimize sharp bends or twists that could stress the fiber cables and impair signal transmission. Follow the manufacturer's recommended bending radius for both the Innerduct and the fiber cables, ensuring that bends are gradual and smooth. Avoid exceeding the maximum pulling tension specified for the fiber cables during installation, as excessive tension can damage the fibers and degrade performance. Use appropriate pulling lubricants and techniques to reduce friction and minimize stress on the cables during installation. Proper routing and handling of the fiber cables within the Innerduct ensure optimal performance and longevity. In addition to physical protection, consider the environmental conditions to which the exposed Innerduct will be subjected. Moisture, dust, and sunlight can all degrade the Innerduct and fiber cables over time, leading to performance issues or premature failure. In damp or humid environments, use moisture-resistant Innerduct and sealing compounds to prevent water from entering the duct and damaging the cables. Consider using UV-resistant Innerduct in areas exposed to direct sunlight to prevent degradation of the material. Regularly inspect the Innerduct and fiber cables for signs of damage or degradation, such as cracks, abrasion, or discoloration. Addressing any issues promptly can prevent further damage and ensure continued reliable performance. Aesthetics are also a consideration, particularly in finished spaces where exposed Innerducts may be visible. While functionality is the primary concern, consider options for concealing or minimizing the visual impact of the Innerduct. Installing the Innerduct along the edge of the room or behind equipment can help to reduce its visibility. Consider painting or covering the Innerduct to match the surrounding environment, blending it in with the decor. These aesthetic considerations can improve the overall appearance of the installation without compromising its functionality or performance. Furthermore, ensure proper grounding and bonding of the Innerduct, especially if metallic components are present, to comply with electrical safety codes and prevent electrical hazards. Grounding and bonding minimize the risk of electrical shock and protect equipment from damage due to electrical faults or surges. Follow the guidelines outlined in the NEC for grounding and bonding of communication cables and equipment, ensuring that all connections are secure and properly sized. Regularly inspect grounding and bonding connections to ensure that they remain intact and effective over time. Finally, proper documentation and labeling of the Innerduct and fiber cables are essential for future maintenance and troubleshooting. Clearly label each segment of Innerduct with its location, cable type, and any other relevant information to facilitate identification and tracing. Maintain accurate records of the installation, including cable routes, termination points, and test results. This documentation serves as a valuable resource for technicians and engineers, enabling them to quickly diagnose and resolve any issues that may arise. By following these additional considerations and best practices, the installation of exposed Innerduct for fiber optic cables can be successfully executed while ensuring compliance with the NEC and maintaining the integrity and performance of the fiber optic network. Fiber optic cables offer significant advantages over traditional copper cables, including higher bandwidth, lower signal loss, and immunity to electromagnetic interference. These characteristics make fiber optic cables ideal for transmitting large amounts of data over long distances, supporting high-speed internet, video streaming, and other bandwidth-intensive applications. Single-mode fiber is designed for long-distance transmission, typically using laser light sources to transmit signals over distances of tens or even hundreds of kilometers. Single-mode fiber has a smaller core diameter than multi-mode fiber, allowing only one mode of light to propagate through the fiber, minimizing signal dispersion and distortion. Multi-mode fiber is typically used for shorter distances, such as within a building or campus, using LED light sources to transmit signals over distances of up to a few kilometers. Multi-mode fiber has a larger core diameter than single-mode fiber, allowing multiple modes of light to propagate through the fiber, resulting in higher signal dispersion and distortion. When selecting fiber optic cables for a specific application, consider the distance over which the signals need to be transmitted, the required bandwidth, and the budget. Single-mode fiber is generally more expensive than multi-mode fiber, but it offers superior performance over long distances. Proper termination and splicing of fiber optic cables are essential for maintaining signal integrity and minimizing signal loss. Fiber optic connectors provide a reliable and repeatable method for connecting and disconnecting fiber optic cables, allowing for easy installation and maintenance. Common types of fiber optic connectors include LC, SC, SINT, and MTP connectors, each with its own advantages and disadvantages in terms of size, performance, and cost. Fusion splicing involves melting the ends of two fiber optic cables together to create a permanent connection with minimal signal loss. Fusion splicing requires specialized equipment and trained technicians to ensure a high-quality splice with minimal defects. Mechanical splicing involves using mechanical connectors to align and join two fiber optic cables without the need for fusion splicing. Mechanical splicing is a faster and less expensive alternative to fusion splicing, but it typically results in higher signal loss. Regular testing and maintenance of fiber optic cables and connectors are essential for ensuring optimal performance and reliability. Optical time domain reflectometers are used to measure the length, attenuation, and reflectance of fiber optic cables, allowing technicians to identify and locate faults or defects in the cable. Power meters and light sources are used to measure the optical power levels of fiber optic signals, ensuring that they meet the required specifications. Cleaning and inspecting fiber optic connectors regularly can prevent contamination from dust, dirt, and other debris, which can degrade signal performance. By understanding the characteristics of fiber optic cables and connectors and following best practices for installation, termination, splicing, and maintenance, the performance and reliability of fiber optic networks can be ensured for years to come. When working with fiber optic cables, safety is paramount. Fiber optic cables transmit light, including infrared light, which can be harmful to the eyes. Never look directly into the end of a fiber optic cable, especially when it is transmitting light. Use appropriate safety glasses or goggles to protect your eyes from accidental exposure to laser light. When handling fiber optic cables, wear gloves to prevent contamination of the fibers with oil, dirt, or other debris. Dispose of fiber optic scraps and debris properly to prevent environmental contamination. Fiber optic cables are made of glass, which can shatter and create sharp fragments. Use caution when handling and cutting fiber optic cables to avoid injury. Ensure that the work area is well ventilated and free from dust and debris to prevent respiratory irritation. Follow all safety guidelines and procedures provided by the manufacturer of the fiber optic cables and equipment. By prioritizing safety when working with fiber optic cables, the risk of injury and environmental damage can be minimized. Fiber optic technology is constantly evolving, with new advancements in materials, components, and techniques emerging regularly. Stay informed about the latest developments in fiber optic technology to improve the performance, reliability, and cost-effectiveness of fiber optic networks. Attend industry conferences, read trade publications, and participate in online forums to learn about new products, technologies, and best practices. Continuously invest in training and education to enhance your knowledge and skills in fiber optic technology. By staying current with the latest advancements in fiber optic technology, you can leverage new innovations to optimize your fiber optic network and meet the evolving demands of your customers. The installation of Innerduct should also adhere to fire safety standards. Select Innerduct materials that are fire resistant and compliant with local fire codes. Ensure that the Innerduct installation does not impede the operation of fire suppression systems or obstruct access to fire exits. Seal any openings or penetrations in fire-rated walls or ceilings with fire-resistant sealant to maintain the integrity of the fire barrier. Install fire stops at regular intervals along the Innerduct run to prevent the spread of fire and smoke. Work with the qualified fire protection engineer to ensure that the Innerduct installation meets all applicable fire safety requirements. By incorporating fire safety considerations into the Innerduct installation, the risk of fire-related damage and injuries can be minimized. Proper planning and design are essential for a successful Innerduct installation. Conduct a thorough site survey to identify potential obstacles, hazards, and environmental conditions that may affect the installation. Develop a detailed installation plan that outlines the cable routes, support locations, and termination points. Coordinate with other trades and stakeholders to ensure that the installation does not conflict with other building systems or operations. Obtain all necessary permits and approvals before starting the installation. Clearly communicate the installation plan to all personnel involved in the project. By investing time and effort in planning and design, the efficiency, safety, and quality of the Innerduct installation can be significantly improved. After completing the Innerduct installation, perform a thorough inspection to verify that all components are properly installed and secured. Check for any signs of damage, such as cracks, abrasion, or deformation. Verify that the Innerduct is properly supported and protected from physical damage and environmental conditions. Test the fiber optic cables to ensure that they meet the required performance specifications. Document the results of the inspection and testing for future reference. Address any deficiencies or issues promptly to ensure that the installation meets all applicable standards and requirements. By conducting a comprehensive post-installation inspection, any potential problems can be identified and resolved before they escalate into more serious issues. Regular maintenance and inspection of the Innerduct and fiber optic cables are essential for ensuring long-term performance and reliability. Establish a periodic maintenance schedule that includes visual inspections, cleaning, and testing. Check for signs of damage such as cracks, abrasion, or corrosion. Clean the fiber optic connectors and cables to remove dust, dirt, and other contaminants. Test the fiber optic cables to verify that they meet the required performance specifications. Repair or replace any damaged components promptly to prevent further degradation. Keep accurate records of all maintenance and inspection activities. By implementing a proactive maintenance program, the lifespan and performance of the Innerduct and fiber optic cables can be maximized.